Tonight, we're going to sit with a genuinely unsettled disagreement at the very center of modern cosmology. One currently being argued, in real time, by two separate teams of credentialed, Nobel-connected scientists, each using some of the most sensitive instruments ever built, each arriving at a different, precisely measured answer to one of the most basic questions we can ask about the universe. How fast is it actually expanding? Here's what most people don't realize about this disagreement. It isn't a case of sloppy measurement, waiting for someone to simply try harder. Both answers are measured with extraordinary precision. Both teams are careful, rigorous, and genuinely confident in their own results. And the gap between those two answers has now survived direct testing by the most powerful space telescope ever built. A test that was specifically designed by the researchers involved with the explicit hope of finally making the disagreement disappear. It didn't disappear. If anything, it got harder to explain away. The first surprise is just how precisely this number has actually been measured. Not once, but twice, using two completely independent methods, each one individually trustworthy, each one refusing to agree with the other. The second surprise is what happened when the James Webb Space Telescope was specifically pointed at this exact question, hoping to catch the simplest, most hoped-for explanation. A straightforward measurement mistake. In the act. It didn't find one. It ruled that explanation out with a level of statistical confidence that would, in almost any other branch of physics, be treated as a confirmed discovery in its own right. The third surprise is that even after that result, the story didn't end. A second, entirely independent team, using an entirely different method, has spent the last 2 years finding results that sometimes seem to close the gap. And then, on closer inspection, don't. And the fourth surprise is what it would actually mean if this disagreement turns out to be real. A universe whose age, whose size, and whose entire future may need to be reconsidered, built on physics we don't yet have. By the end of tonight, you're going to understand exactly what the Hubble tension actually is, why a Nobel Prize-winning discovery from 1998 sits at the very center of the story, what James Webb genuinely did and didn't settle when astronomers finally pointed it at the problem, and why, as of the most recent research available, nobody, not one credentialed scientist on either side of this debate, can yet tell you which number is correct. Before we dive in, if you're someone who finds real comfort in this kind of patient, honest exploration of the universe, who trades the noise of the day for a little cosmic perspective before sleep, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Let's start with where this all began, because the original discovery, a century ago, was never supposed to become a crisis at all. In the 1920s, the astronomer Edwin Hubble measured distances to a handful of distant galaxies, using a specific class of star called Cepheid variables, pulsating stars whose brightness rises and falls in a predictable, measurable rhythm. Combining those careful distance measurements with separate observations of how each galaxy's light was redshifted, stretched toward longer wavelengths, Hubble showed something genuinely remarkable. Galaxies, on average, are receding from us at a rate directly proportional to how far away they already are. It was the discovery that the universe itself is expanding. Hubble's own original measurement of exactly how fast that expansion was happening was, by modern standards, genuinely rough. Not accurate to better than a factor of 2, limited by interstellar dust he didn't fully account for, and by the resolution limits of 1920s telescopes. Nobody at the time expected that number to eventually become one of the most contested figures in all of physics. The modern version of this same measurement is called the Hubble constant, written as h0, and expressed in a slightly unusual unit, kilometers per second per megaparsec. Essentially, how much faster a galaxy appears to be receding from us for every additional unit of distance separating us from it. Over the following century, that number was refined, generation after generation, by increasingly careful astronomers using increasingly capable instruments. And by the 2010s, two entirely independent, genuinely high-quality methods for measuring it had each become precise enough that something new and genuinely alarming began to happen. They started disagreeing with each other by more than their own stated margins of error should allow. That disagreement, not Hubble's original 1920s discovery, is the actual crisis tonight's story is about. Here are the core numbers, stated with real precision, because the specificity matters. Methods that infer the expansion rate from the early universe, from the afterglow of the Big Bang itself, currently give a value of 67.4 kilometers per second per megaparsec, plus or minus just half a unit based on Europe's Planck satellite. Methods that measure the expansion rate directly, using nearby, present-day objects, currently cluster around 73.0 to 73.5 kilometers per second per megaparsec, with individual studies reporting uncertainties as tight as half a unit to 1 full unit. It's worth being honest about the most accurate and most interesting way to frame this story from the very beginning. This isn't really a tale of scientists not knowing how fast the universe expands. Both numbers are measured with real, genuine precision. It's a tale of two trustworthy, independently verified methods, each one individually very precise, disagreeing with each other by more than their combined uncertainties should reasonably allow. Which is a considerably more interesting and considerably more honest kind of mystery than simple ignorance would be. Before we can properly understand why this specific number causes so much trouble, we need to understand the broader model it sits inside, because the Hubble constant isn't measured in isolation. It's deeply entangled with everything else cosmologists currently believe the universe is actually made of. The standard cosmological model, called lambda cold dark matter, or LCDM for short, describes the universe's total energy content in three broad categories. Roughly 5% is ordinary, baryonic matter. Everything we have ever directly observed, in any form, every star, every planet, every living thing, including every single one of us. Roughly 27% is dark matter, a form of matter that interacts gravitationally, shaping how galaxies rotate and how light bends around massive clusters, but that has never once interacted with light directly, and has never been directly detected in any laboratory on Earth. And roughly 68% is dark energy, the still unexplained force behind the accelerating expansion of the universe, a discovery we're about to spend real time with tonight, represented in the standard model by the Greek letter lambda as a cosmological constant. Put those three figures together, and the honest, somewhat humbling summary is this. Roughly 95% of the universe's total energy content is not directly understood at any fundamental level. Dark matter and dark energy are both named, quite literally, for what they are not. Visible, understood, rather than for what they actually, physically are. Here's why this composition question connects directly to tonight's central mystery. The Hubble constant, on the early universe side of the measurement, isn't read off directly from raw data. It's derived by fitting observations to the LCDM model itself, a model that assumes specific proportions of ordinary matter, dark matter, and dark energy from the very start, which means any hidden error in those assumed proportions could directly, quietly bias the entire early universe estimate of H0. And this is precisely why new, currently unaccounted for physics hiding somewhere in the dark sector, remains one of the leading categories of proposed explanations for the entire tension, a thread we'll return to in real depth later tonight. Picture the universe's entire energy content as a single dinner plate. The ordinary matter making up every star, every planet, and every living thing that has ever existed anywhere would cover an area on that plate smaller than a single coin, resting on its edge. Here is the actual heart of tonight's mystery. Two genuinely independent methods, each one measuring the exact same quantity, using completely different data, completely different assumptions, and completely different eras of cosmic history, and stubbornly refusing to agree. The first method looks at the early universe directly. Europe's Planck satellite, operating from 2009 to 2013, mapped the cosmic microwave background. The faint, ancient light released roughly 380,000 years after the Big Bang itself, the earliest light that exists anywhere in the universe, in extraordinary detail. By carefully fitting the tiny, precisely measured temperature variations scattered across that ancient light to the full LCDM model, cosmologists can calculate what the present-day expansion rate should be without ever directly observing anything nearby at all. It's an inference, built entirely from conditions in the deep past, projected forward across the entire history of the universe. Planck's own legacy result, 67.4 kilometers per second per megaparsec, plus or minus half a unit. The second method looks at the local, present-day universe directly and climbs what astronomers call the cosmic distance ladder, a careful, staged sequence of measurements, each rung calibrating the next. It begins with geometric parallax measurements of nearby stars, calibrated to extraordinary precision by the European Gaia satellite, achieving roughly 1 to 2% precision across more than 100,000 individual stars. Those precisely known distances calibrate the true, intrinsic brightness of Cepheid variable stars, the same class of pulsating star Hubble himself originally used, whose brightness and pulsation period are tightly, predictably related, a relationship first discovered by the astronomer Henrietta Leavitt in the early 1900s. Cepheids found in galaxies that also happen to host a specific, extremely bright, remarkably consistent kind of stellar explosion, type Ia supernovae, used throughout astronomy as reliable standard candles, then calibrate the supernovae's own true brightness in turn. And those calibrated supernovae, visible across far greater distances than any individual Cepheid, extend the entire ladder outward to cosmologically significant scales. The current leading result from this method, produced by a research collaboration called SH0ES, stands at 73.04 kilometers per second per megaparsec, plus or minus 1.04, based on a comprehensive 2022 combined analysis. The two methods genuinely look at fundamentally different errors and fundamentally different distances. The cosmic microwave background method infers today's expansion rate from conditions roughly 13.8 billion years in the past. The distance ladder method measures it directly from objects sitting in the relatively nearby, present-day universe. Neither method has any obvious, built-in reason to simply be wrong on its own terms, which is precisely what makes their persistent disagreement genuinely significant, rather than a simple mistake quietly waiting to be discovered and corrected. Here's the actual size of the gap, stated plainly. Roughly 73 versus roughly 67 works out to about a 9% difference. Small enough, on its face, to sound like a minor rounding discrepancy. But given how tightly both individual results are measured, that 9% gap translates into a statistical separation of more than 5 standard deviations in most rigorous analyses. A level of statistical confidence that, in particle physics, would ordinarily be treated as the confirmed discovery of something genuinely new, rather than dismissed as coincidence or measurement noise. This is shocking discovery number 1. Two of the most carefully measured, most independently verified numbers in all of modern cosmology, each one individually trustworthy, simply do not agree with each other. And the size of that disagreement is large enough that chance alone is no longer a serious, credible explanation. Here's where tonight's title earns itself directly, because one of the two scientists at the very heart of this ongoing disagreement already holds a Nobel Prize for a related but genuinely distinct discovery. Adam Rees shared the 2011 Nobel Prize in Physics with Saul Perlmutter and Brian P. Schmidt, awarded specifically for the discovery of the accelerating expansion of the universe through observations of distant supernovae. That prize honored a 1998 discovery made using the High-Z supernova search team, led by Rees and Schmidt, working independently and near simultaneously alongside a separate collaboration, the Supernova Cosmology Project, led by Perlmutter. Both teams, working from different data, converged on the exact same, genuinely shocking conclusion. The universe's expansion isn't merely continuing, it's actively accelerating. It's worth being precise about a distinction that matters directly for tonight's story. That Nobel-winning 1998 work established that the universe's expansion is accelerating at all, proving, in the process, that dark energy must genuinely exist in some form. Ries's later, separate, ongoing research project called SH0ES, an acronym for supernova H0 for the equation of state, uses similar Type Ia supernova data, extended with careful Cepheid calibration, specifically to measure the precise present-day value of the Hubble constant, the exact number currently in dispute. The Nobel Prize itself was not awarded for discovering the Hubble tension, but the same underlying data, the same underlying techniques, and the same lead researcher connect both stories directly together. Ries's original 1998 paper, built from just 10 Type Ia supernovae observed at various cosmological redshifts, has accumulated roughly 28,000 citations as of late 2025, placing it among the single most cited papers in all of modern astrophysics. And Ries himself remains a genuinely active public communicator on this exact topic. As recently as January 2026, he delivered a public lecture at UC Davis, walking a general audience through the standard candle and redshift methods underlying his own work, and he continues to actively publish and comment on new James Webb Space Telescope results as they emerge. Results we're about to spend considerable time with directly. Here is the moment tonight's title genuinely, honestly earns itself. Before James Webb ever turned its instruments toward this specific question, one of the most prominent, most widely hoped-for explanations for the entire Hubble tension involved something called crowding, a specific, well-understood kind of systematic measurement error. In a sufficiently crowded field of background stars, a single target Cephid's measured light can become subtly contaminated by unresolved, overlapping stars sitting directly behind or beside it in the same crowded patch of sky. An effect that could, in principle, quietly bias its measured brightness, and therefore its calculated distance, throwing off the entire distance ladder calculation built on top of it. James Webb, with roughly 4 times the raw resolution and roughly 10 times the near-infrared sensitivity of the Hubble Space Telescope, was specifically capable of re-observing a subsample of the exact same Cepheids Hubble had originally used, cleanly resolving each one from its surrounding background contamination for the very first time in the history of this measurement. The result, published by Ries and his collaborators in 2023, and confirmed again in follow-up analyses through 2024 and 2025, landed with genuine, unambiguous clarity. James Webb's re-observations agreed with Hubble's own original Cepheid measurements to within roughly 1 standard deviation. SH0ES's own James Webb data achieved as much as a 2.5-fold reduction in the overall scatter of the underlying Cepheid brightness period relationship, with no evidence of the feared crowding effect showing up at high statistical confidence. A comprehensive 2025 analysis placed this finding at somewhere between 7 and 8 standard deviations of confidence that distance-dependent measurement bias is not, in fact, the explanation for the tension. This was a genuinely important, genuinely unambiguous result, and it's worth sitting with directly. It ruled out the simplest, most hoped-for explanation. A straightforward instrumental measurement error, quietly baked into Hubble's original Cepheid photometry, as the actual source of the entire disagreement. Whatever is genuinely causing the persistent 67 versus 73 gap, it is now very unlikely to be a simple, correctable Cepheid measurement mistake of exactly the kind astronomers had most hoped to find. This is precisely the moment where maybe it's just a straightforward measurement error somewhere stopped being a live, simple, comforting possibility, which is exactly why the tension became more genuinely interesting and more actively debated in the years that followed, rather than less. This is shocking discovery number 2. The single most powerful telescope humanity has ever built was specifically pointed at the most hopeful, most mundane explanation for this entire mystery. And instead of finding a fixable mistake, it confirmed, with genuinely striking statistical confidence, that the mistake almost certainly isn't there at all. Ruling out simple Cepheid measurement error didn't end the story, because a second, genuinely independent local universe method exists, built on an entirely different class of star, and it has produced its own genuinely complicated, genuinely evolving results across the past 2 years. The method is called the tip of the red giant branch, or TRGB, a technique that uses red giant stars at a very specific, predictable, well-understood stage of their own stellar evolution as a distance calibrator, entirely independent of Cepheid variables altogether. Astronomer Wendy Friedman of the University of Chicago leads a research collaboration called the Chicago-Carnegie Hubble Program, or CCHP, which has spent decades developing TRGB, and a related third method using a class of star called J-region asymptotic giant branch, or JAGB, stars, specifically as an independent cross-check against the entire Cepheid-based distance ladder. In August 2024, Friedman's team published a James Webb-based TRGB study examining 11 separate galaxies, producing a value for the Hubble constant between 68.4 and 71.5 kilometers per second per megaparsec, sitting squarely between the CMB figure and SH0ES's own local figure, and, in the study's own careful language, not offering strong support for the idea that genuinely new fundamental physics is actually required. The result received widespread, prominent coverage, much of it suggesting the tension might finally be resolving. Rias's own on-record response was direct. He told Quanta magazine that Friedman's analysis relied on what he described as such a small supernova sample that it risked giving a somewhat misleading impression of the true Hubble constant value, while also, notably, acknowledging that the underlying distance measurements themselves were in excellent agreement with SH0ES's own prior work. A more technical, genuinely important joint finding is worth including in real detail, because it clarifies exactly where the disagreement actually lives. A direct comparison using a single common calibration anchor. A specific, well-studied galaxy called NGC 4258, across 8 separate combinations of methods, samples, and telescopes, drawing on James Webb Cepheids, TRGB, and JAGB measurements from both the SH0ES and CCHP teams, plus additional Hubble-based TRGB and mirror variable star data, found that the underlying individual distance measurements themselves actually agree with each other to within roughly 1 standard deviation. A mean difference of only about 0.03 magnitudes, considerably smaller than the roughly 0.18 magnitude difference that would be needed to fully explain the entire Hubble tension. What this genuinely suggests is that the roughly 2.5 km per second per megaparsec gap between CCHP's James Webb-based result and the full SH0ES samples result appears to be driven mainly by which specific galaxies and supernovae each team chooses to include in their own final analysis. A question of sample selection, rather than any fundamental disagreement between the Cepheid and TRGB measurement techniques themselves. In June 2025, Friedman's team, incorporating additional Hubble Space Telescope data alongside their James Webb observations, updated their own figure to 70.4 km per second per megaparsec, with a roughly 3% uncertainty. A value they themselves describe as bringing their result into genuine statistical agreement with Planck's own 67.4. Friedman's own candid, on-record account of how genuinely unsettled this entire process has felt from the inside is worth including directly. She has described the experience of watching her own earlier analysis appear to have, in her words, killed the Hubble tension, only to watch it, in her own words, come roaring back to life as further scrutiny and community analysis continued. The SH0ES team's own response to the sample selection critique arrived in a subsequent analysis, using the complete Hubble plus James Webb TRGB sample, deliberately designed to remove exactly the kind of sample selection artifact the joint comparison had identified. That analysis still found a Hubble constant of 72.1 to 73.3, plus or minus 1.8. landing close to SH0ES's own original Cepheid-based value, rather than converging toward Friedman's own lower figure. And the most recent, most comprehensive SH0ES aligned combination located for this exact research, published by Rees and collaborators in 2025, combining Hubble and James Webb Cepheid data with 35 separate TRGB calibrations across 55 individual Type Ia supernovae, arrived at 73.18 km per second per megaparsec, plus or minus just 0.88, described in the same analysis as yielding almost 6 sigma tension when compared directly against Planck. Here is the fair, genuinely honest summary worth carrying forward. Friedman's team has consistently found somewhat lower Hubble constant values than SH0ES using TRGB, and their results genuinely do sit closer to the early universe, CMB-based prediction. This remains a real, respected, professionally credentialed minority position within cosmology, not a fringe claim to be dismissed. But as of the most recent research located for tonight's exploration, the broader weight of available evidence, including SH0ES's own response using their complete sample, additional independent methods we're about to walk through directly, and multiple comprehensive 2025 and 2026 review papers, has not shifted decisively toward Friedman's lower value being the final, settled answer. Both positions remain genuinely live, and are both being actively, seriously defended by credentialed, working research teams right now, tonight. Given that Cepheids and TRGB stars, the two leading local universe methods, disagree with each other by a meaningful margin, it's worth asking whether any genuinely independent method exists, one that doesn't rely on either technique at all. The most conceptually elegant of these arrived on August 17, 2017, when the LIGO and Virgo gravitational wave detectors recorded GW170817, a collision between two neutron stars, which was also, remarkably, observed directly through conventional light. A gamma-ray burst arriving just 2 seconds after the gravitational wave signal itself, followed by a visible optical afterglow located near a specific galaxy called NGC 4993. It was the first ever multi-messenger gravitational wave event in the history of astronomy. Because a gravitational wave's own signal directly encodes the physical distance to its source, without requiring any calibrated standard candle at all, this single event allowed astronomers to calculate a genuinely, completely independent measurement of the Hubble constant. It's worth being honest that this one event remains, as of the most recent research available, essentially the only truly clean multi-messenger standard siren detection ever recorded. No directly comparable event has occurred again since 2017, which meaningfully limits how precise this particular method can currently be. More recent combined analyses, incorporating gravitational wave catalogues alongside weak lensing and galaxy survey data published in January 2026, give values with genuinely large associated uncertainty, a result of roughly 67.9, with an error range spanning from about plus 4.4 to minus 4.3, a measurement precision of roughly 6.4%, a range wide enough to remain consistent with either side of the ongoing tension. Other, considerably more speculative combined analyses incorporating lensed gravitational waves alongside newer time delay lensing catalogues have produced quite different central values with even wider associated uncertainty. One 2026 study reported a central value of nearly 84 with an error range wide enough, roughly 13.5%, that it genuinely doesn't meaningfully favour either the roughly 67 or roughly 73 camp, and shouldn't be presented as a strong data point on either side of this debate. A separate, genuinely powerful independent technique is called time delay cosmography, sometimes described more simply as gravitationally lensed distance measurement. When a distant, variable light source, a quasar, or occasionally a supernova, happens to sit directly behind an intervening galaxy, that galaxy's own gravity can bend and split the background light into multiple separate images. Because those different light paths travel slightly different total distances to reach us, the different images arrive with a measurable time delay between them. And combining that time delay with a careful physical model of the lensing galaxy itself yields a direct, purely geometric distance measurement entirely independent of the full Cepheid and supernova distance ladder chain altogether. Research collaborations including H0 LICOL and its successor project TDCOSMO have used exactly this method for years. A December 2025 study led by a University of Tokyo team using newly refined lens measurements produced results that, according to the announcing press release itself, deepen the Hubble tension mystery rather than resolve it, continuing to favor a value closer to the local, roughly 73 side of the disagreement. A separate lensed supernova measurement reported in 2024 found a Hubble constant of 75.4, notably on the higher end of the entire local universe range currently under discussion. And a final, genuinely elegant independent method uses something called megamasers, naturally occurring, extraordinarily bright microwave-emitting regions found surrounding the supermassive black holes at the centers of a small handful of specific galaxies. These megamasers allow an extremely precise, entirely geometric distance measurement, requiring no standard candle calibration of any kind whatsoever. The best studied example, the same galaxy NGC 4258 we encountered a moment ago in the TRGB comparison, has a maser-based distance measured at 7.60 megaparsecs, with a combined uncertainty of roughly 0.17 to 0.15 megaparsecs. Combined with separate Cepheid measurements taken in that exact same galaxy, this yields a Hubble constant of 72.0, plus or minus 3.0, once again landing on the higher, local universe side of the tension, though with somewhat wider uncertainty than the leading Cepheid and TRGB results we've already walked through directly. The honest synthesis worth carrying forward from this entire section. Independent methods beyond Cepheids and TRGB stars represent a genuinely promising path toward eventually settling this disagreement without relying on either team's own specific technique. But as of the most recent research available, most of them, gravitational wave standard sirens especially, still carry uncertainties too large to be genuinely decisive on their own. Meanwhile, the methods precise enough to actually matter, lensing and megamaser distances, tend to land considerably closer to the local, roughly 72 to 75 side of the disagreement, rather than toward the CMB's own 67.4 figure, though not yet with quite the overwhelming statistical precision of the leading Cepheid and TRGB results. Assume, for a moment, that this entire disagreement isn't a measurement error at all, that both numbers are genuinely, correctly measured, and the universe itself is simply behaving in a way our current standard model doesn't yet properly account for. What would that actually mean? The leading category of proposed explanation involves what researchers call late universe solutions. The idea that dark energy itself isn't a genuinely fixed, unchanging constant, the way the standard LCDM model currently assumes, but instead slowly evolves over the course of cosmic history. This possibility is often described using an evolving dark energy equation of state, typically parameterized using two separate numbers describing dark energy's present-day value and its overall rate of change over time. It's genuinely important to understand that this isn't purely abstract theoretical speculation. The DESI collaboration, the Dark Energy Spectroscopic Instrument, released detailed 2024 and 2025 data on baryon acoustic oscillations, a specific precisely measurable pattern of ancient sound waves frozen into the large-scale structure of the universe, and independently found genuine evidence, reaching as high as 4.2 to 5 standard deviations of statistical significance in some combined analyses, for exactly this kind of deviation away from a perfectly constant dark energy density. A finding one physics news outlet directly described as having rocked the cosmology world. A natural, actively pursued question immediately follows. Could the exact same new physics behind DESI's own evolving dark energy signal also directly explain the Hubble tension? A comprehensive 2026 study tested 5 separate cosmological models: standard LCDM, a modified WCDM version, a more flexible W0-way CDM version, a scalar field dark energy model called Phe-CDM, and a genuinely interacting dark energy model, against combined DESI, cosmic microwave background, and supernova data simultaneously. Their finding was genuinely striking. The Hubble constant inferred from the combined data consistently aligned with early universe, CMB-based measurements across every single model they tested, meaning none of these specific dark energy modifications, taken entirely on their own, actually resolved the Hubble tension at all, even though that same analysis did find genuinely compelling evidence for the underlying DESI dark energy evolution itself. A very recent, methodologically careful reanalysis published in July 2026, specifically testing this exact same question, reached a genuinely similar conclusion, memorably summarized in its own coverage as, "Dark energy flips its sign, but the Hubble tension refuses to budge," finding real, if partial, support for evolving dark energy models, while simultaneously confirming that the Hubble tension itself remains genuinely, statistically unresolved regardless. A separate category of proposed solution, called early universe solutions, instead proposes modifying the underlying physics before the cosmic microwave background was ever released. Roughly the first 380,000 years of the universe's entire existence. The most commonly discussed version involves something called early dark energy, hypothetical additional energy component, active only briefly during that earliest window, which would slightly shrink a specific, precisely calculable distance scale called the sound horizon, imprinted directly into the cosmic microwave background, that the entire early universe Hubble constant calculation ultimately depends on. Shrinking that sound horizon within the model would push the CMB inferred Hubble constant upward toward the local value. It's genuinely worth flagging that this entire class of solution remains actively studied and genuinely contested. No early dark energy model proposed so far has achieved the combination of precision and internal consistency needed for broad scientific acceptance, and some specific analyses find that easing the Hubble tension this way creates new tension with other cosmic microwave background parameters. Instead, a genuinely creative, very recent proposal, published in January 2026 in the journal Nature Astronomy by a Simon Fraser University-led research team, suggests that faint primordial magnetic fields, present since the universe's very earliest moments, could potentially explain both the Hubble tension and the otherwise unexplained origin of the cosmic magnetic fields we currently observe throughout galaxies and galaxy clusters today. A genuinely elegant, unifying idea, if it holds up. The research team describes their proposal as surviving, in their own words, the most detailed and realistic tests available today, drawing on Hubble, Planck, and other telescope data, while being fully explicit that genuinely confirming or ruling out the idea will require several more years of dedicated future observation. A further, smaller, more contested category involves modified gravity theories. Altering Einstein's own general relativity directly at genuinely cosmological scales, rather than introducing any new energy component at all. This category generally faces steeper, more demanding observational constraints than the dark energy-based approaches we've already covered. Per a comprehensive 2026 review of this entire decade-long debate, The reason none of these proposed solutions has yet achieved genuine scientific consensus is that most currently viable, full solutions appear to require either correlated changes to both early universe and late universe physics simultaneously, or entirely new physics specifically describing the transition between small-scale cosmic structure and the universe's own eventual large-scale uniformity, meaning a single, simple, one-parameter fix looks increasingly unlikely. If the tension is eventually confirmed as genuine new physics, rather than a persistent, still-hidden systematic error, the eventual answer may well require several coordinated modifications to the standard cosmological model at once, rather than any single, tidy correction. The Hubble constant isn't simply an abstract number describing cosmic expansion in isolation. It's directly, mathematically tied to the universe's own total age. In a simplified model, the universe's age works out to roughly 1 divided by the Hubble constant, with additional corrections applied for the universe's precise matter and dark energy content. A higher measured value for H0 implies the universe has been expanding faster overall, which, all else being equal, implies it reached its current observed size in less total time, meaning a genuinely younger universe. A lower measured value implies the opposite, a genuinely older one. Using Planck's own figure of 67.4, within the complete standard LCDM model, the universe's total age calculates out to approximately 13.8 billion years. The figure most people are already broadly familiar with. Using SH0ES's higher local value instead, within that same overall modelling framework, would push the implied age modestly younger, though the exact size of that shift genuinely depends on which other cosmological parameters, like matter density and dark energy density, are held fixed versus allowed to adjust alongside it, since recalculating the universe's total age isn't a simple, one-line mathematical inversion of the Hubble constant taken entirely on its own. This is precisely why genuinely resolving this tension matters for considerably more than simply getting one number right. The Hubble constant functions as a load-bearing parameter throughout the entirety of modern cosmology, feeding directly into calculations of the universe's total age, its overall size, the detailed timeline of when the very first stars and galaxies actually formed, and the calculated distances to essentially every significant astronomical object beyond our own immediate galactic neighborhood. A confirmed, genuinely real discrepancy at this specific foundational level would ripple outward through a considerable portion of modern astrophysics distance and timeline calculations all at once. If dark energy genuinely continues to behave as a true, fixed cosmological constant indefinitely into the deep future, the accelerating expansion first discovered back in 1998 will simply continue, uninterrupted, eventually coming to dominate the universe's own long-term fate entirely. A scenario commonly described as heat death, or sometimes the big freeze. Under this specific scenario, over a span of trillions of years, galaxies that aren't already gravitationally bound to our own local group will accelerate away from us faster than light itself can ever bridge the continuously widening gap between us, eventually vanishing from observability entirely. A genuinely strange future in which the observable universe itself effectively shrinks in terms of what remains reachable or even detectable, even as the underlying fabric of space itself continues expanding without limit. Star formation throughout the universe will gradually exhaust its available supply of hydrogen fuel, a decline already well underway, having peaked billions of years in the past. On timescales of roughly 10 to the 14th power years, the very last stars still burning anywhere in the universe will finally burn out entirely. Stellar remnants, white dwarfs, neutron stars, and black holes will persist for a very much longer stretch of time still, with even proton decay itself, if it genuinely occurs at all, a physical process that remains entirely unconfirmed as of current physics, potentially unfolding across timescales as long as 10 to the 34th power years or considerably more. black holes themselves would eventually, gradually evaporate entirely through a slow quantum process called Hawking radiation across almost unimaginably long stretches of cosmic time, before the universe finally settles into a cold, dark, maximally diffuse, essentially featureless final state. It's genuinely worth flagging directly that this entire long-term scenario is conditional on one specific assumption: that dark energy continues behaving as a genuinely fixed constant indefinitely, forever. That is precisely the exact assumption DESI's own 2024 and 2025 evolving dark energy evidence, which we walked through a moment ago, directly calls into serious question. If dark energy is genuinely evolving over cosmic time rather than remaining perfectly constant, the true long-term fate of the entire universe becomes, once again, a genuinely open question. Not the settled, familiar heat-death conclusion so many popular explanations confidently present. This far-future scenario remains the standard, most commonly cited version of our cosmic future, but it rests directly on an assumption current, active research is genuinely re-examining in real time, right now. Given how genuinely fast-moving this entire story has been, it's worth walking through the actual back and forth chronologically, because the honest answer to, has this been resolved, has genuinely swung more than once in just the past 2 years. In August 2024, Friedman's James Webb-based TRGB study, producing a value between 68.4 and 71.5, prompted widespread coverage suggesting the tension might finally be resolving. In June 2025, Friedman's own updated figure of 70.4, plus or minus 3%, continued that same broader narrative, with one prominent outlet running a piece directly titled, "Is the Hubble tension starting to go away?" But in April 2025, a considerably more skeptical piece, appearing in Scientific American under the title, "The Hubble tension is becoming a Hubble crisis," covered a separate, new independent measurement described as having genuinely strengthened the overall case for the tension being real, quoting one researcher's own on-record assessment that, "We've been at this Hubble tension level for a long time." In December 2025, the University of Tokyo-led gravitational lensing study we covered directly a moment ago was announced with coverage explicitly describing it as deepening, rather than resolving, the underlying mystery. In January 2026, the Simon Fraser University-led primordial magnetic field proposal was announced, explicitly and honestly framed by its own authors as promising, but genuinely requiring several more years of dedicated observation before it could be meaningfully confirmed either way. Through March and April of 2026, a comprehensive multi-model analysis testing 5 separate dark energy variants against the newest available DESI, cosmic microwave background, and supernova data simultaneously, found the underlying tension persisting across every single model tested. Separately, during that same window, a large, community-built distance measurement collaboration achieved roughly 1% overall precision, landing at approximately 73.5, plus or minus 0.7 to 0.8, and reported the underlying discrepancy as, if anything, genuinely harder to attribute to simple systematic error than it had appeared previously. And in July 2026, the most recent source located for tonight's exploration, a rigorous statistical re-examination specifically testing whether DESI's own evolving dark energy signal could genuinely explain the Hubble tension, concluded that standard LCDM earns a real but partial victory in certain specific tests, while the underlying Hubble tension itself, in the study's own words, remains stubbornly unresolved. The overall, genuinely honest synthesis, as of the most current sources available for tonight's exploration: the Hubble tension has not been resolved, and the overall weight of 2025 and 2026 evidence, including independent lensing measurements, the highest precision distance ladder combination yet achieved by any research team, and dedicated theoretical tests of the leading evolving dark energy connection. continues to favor this genuinely being a real, currently unexplained discrepancy, rather than a hidden measurement artifact quietly waiting to be found and corrected. Friedman's CCHP team's own consistently lower TRGB-based values remain a genuine, actively and seriously defended minority position within the broader field, not a discredited one. This remains a genuinely live scientific disagreement between two credentialed, respected research groups, not a settled dispute with a clear winner. And it would be inaccurate, based on everything currently available, to present either side as having definitively won this argument. Before we close, let's gather everything we've walked through tonight and sit with the true scale of how thoroughly this specific disagreement has actually been tested. Two numbers, 67.4 and somewhere between 72 and 73.5, each one measured with genuine, hard-won precision, each one built from decades of careful, patient astronomical work. A statistical separation exceeding 5 standard deviations, tested directly against James Webb's dramatically improved resolution, specifically hoping to catch a simple measurement error, and instead confirming to 7 or 8 standard deviations of confidence that the simple explanation almost certainly isn't there. A second independent method, using an entirely different class of star, producing results that have shifted, been challenged, been defended, and shifted again across less than 2 years of continuous, careful scrutiny. Independent cross-checks using gravitational waves, gravitational lensing, and naturally occurring cosmic mazes, mostly landing closer to the higher, local universe figure, though not yet with quite enough precision to be fully decisive on their own. And an entire cluster of proposed theoretical explanations, evolving dark energy, early dark energy, primordial magnetic fields, modified gravity. Each one actively studied, none of them yet achieving genuine scientific consensus. Two of the researchers whose work sits directly at the center of this entire story, Adam Rees and, by an entirely separate, independent route decades earlier, Saul Perlmutter, already share a Nobel Prize for a related discovery: the very existence of dark energy itself. That was, in 1998, a complete, total surprise to the very scientists who first found it. It's genuinely worth remembering that surprise, because it's the same field, working the same way, still doing exactly what it did then, measuring carefully, checking rigorously, and refusing to pretend a genuine disagreement is settled before the evidence actually supports it. There's something genuinely worth sitting with here, now that we've walked through this entire disagreement together, from its origins in Hubble's own rough 1920s measurement all the way through to July 2026's most recent, still genuinely unresolved analysis. It's tempting, listening to a story like this one, to want it to end with a single, clean answer. One number, finally, definitively agreed upon by everyone involved, closing the file for good. But the more honest place to actually leave this story, and in its own quiet way, the more genuinely comforting one, is simply this: the universe is under no obligation whatsoever to resolve itself on any human researcher's own preferred timeline, or on any single documentary's own particular runtime. Two careful, rigorous, genuinely well-funded teams of scientists, using some of the most sensitive scientific instruments ever built by our species, currently disagree, in good faith, about one of the single most basic numbers describing physical reality itself. And rather than quietly papering over that disagreement, or picking a preferred side and simply moving on, the field's actual response has been to build even better instruments, design even more careful, more deliberately independent tests, and simply keep checking. That ongoing, genuinely unresolved checking is not, in any sense, a failure of cosmology as a discipline. It is, quite precisely, what a living, healthy science, still carefully doing its actual job, genuinely looks like from the inside: patient, rigorous, willing to be surprised, and honest enough to say, clearly and directly, exactly how much remains genuinely unknown. there's a deeper thread worth pulling on here too. Every single number in tonight's story, 67.4, 73.04, 70.4, 72.1, 73.18, represents years of somebody's own careful, patient work, building an instrument, calibrating a telescope, checking a calculation twice, and then a third time, defending a result honestly against genuine, good faith criticism from equally careful colleagues. The disagreement between these numbers isn't evidence that any of that work was done poorly. It's evidence that the universe itself is subtler and considerably stranger than any single one of our current models has yet fully captured, and that the people doing this work know it and keep working anyway. Picture it one last time before we close tonight. Somewhere, right now, a satellite is still patiently studying the faint, ancient afterglow of the Big Bang itself, refining a single number, 67.4. Somewhere else, an entirely different team is still carefully measuring the brightness of pulsating stars in distant galaxies, refining a different number, somewhere close to 73. Both teams are right, by every standard their own careful methods can offer. Both numbers are true, within their own honestly stated uncertainties. And neither team has yet found the missing piece that would make them agree. James Webb, the most powerful telescope our species has ever built, was pointed directly at this exact disagreement, hoping to make it quietly disappear. It didn't disappear. It became more precisely, more confidently, more honestly unresolved. The easy explanation ruled out, the hard mystery left standing, more clearly visible than it had ever been before. Somewhere in that gap between 67 and 73, in that small, stubborn, statistically undeniable disagreement, may sit an entirely new piece of physics, a dark energy that changes over time, a field from the universe's earliest instance nobody has yet directly detected, some genuinely new interaction between the visible universe and the 95% of it we still can't directly see. Or it may sit somewhere far more mundane, a subtle bias in a decades-old calibration, still waiting, patiently, to finally be found. Nobody currently knows which. And the honest scientists on both sides of this exact disagreement will tell you exactly that, directly, without hesitation, whenever you ask them. We are, right now, tonight, living inside an unfinished universe. Not because our instruments have failed us, but because they have finally become good enough to reveal a genuine seam in our own understanding, one careful measurement at a time. That is not a small thing to be alive for. It is, in its own quiet way, one of the more remarkable moments in the entire history of trying to understand where we actually live. Tonight we sat with the Hubble tension, a genuine, ongoing disagreement between two of the most carefully measured numbers in all of modern cosmology, and the Nobel Prize-connected story sitting directly at its center. We found that the universe's expansion rate, first roughly measured by Edwin Hubble in the 1920s, has now been measured twice by two entirely independent, genuinely trustworthy methods. One looking at the ancient afterglow of the Big Bang, the other measuring nearby stars and galaxies directly, and that these two methods disagree by more than 5 standard deviations, a gap too large, by the standards of rigorous physics to comfortably attribute to simple chance. We found Adam Rees and his Nobel Prize-winning 1998 discovery of the universe's accelerating expansion sitting directly behind today's ongoing measurement effort, and we found James Webb specifically tasked with testing the most hopeful explanation for the entire disagreement, only to rule that explanation out with genuinely striking statistical confidence. We found a second independent method, using an entirely different class of star, producing its own genuinely evolving, occasionally conflicting results across the past 2 years. A real scientific disagreement, conducted in good faith, between two credentialed, respected research teams, neither one currently able to claim final victory. We found independent cross-checks, using gravitational waves, gravitational lensing, and naturally occurring cosmic masers, mostly, though not yet decisively, favouring the higher, local universe measurement, and we found an entire cluster of genuinely serious proposed explanations. Evolving dark energy, early dark energy, primordial magnetic fields, modified gravity. Each one actively studied, none of them yet accepted as the field's final, settled answer. None of this is a story about science failing. It's a story about science working exactly as it should, measuring carefully, testing rigorously, and refusing to declare victory before the evidence genuinely supports it. The universe's true expansion rate, a number that determines its age, its size, and its ultimate fate, remains, as of tonight, honestly, genuinely unresolved. Sleep well tonight, knowing that somewhere above you, two entirely different numbers are quietly, patiently waiting for someone to finally explain why they don't agree, and that the not knowing, right now, is simply what an honest, living universe still looks like from here. Good night, and rest well under a sky whose exact speed and whose exact age we are still carefully together working out.